Okay, this chapter deals completely with gases. Now, we know that gases is one of the three states of matter. There's solids, liquids, and gases. And what we have to realize about a gas, it's very special. Well, like a liquid, a gas takes the shape of its container, and so does a liquid. You know, if you pour it on the floor, it's over the whole floor. If it's in a round glass, the liquid is round. A square glass is square. And a gas would do the same thing, but a gas also takes the volume of its container. So if you have a liter of a gas, and you open that liter container, that gas is then going to fill the room, and it's going to occupy the entire volume of the room. So when you define a gas as a certain volume, that's really not telling you how much of that gas it is, because you can have the same number of gas molecules occupying a liter as you could occupying an entire room. So we have another variable that we have to use to determine how much of a gas we have, and that's pressure. And a little bit about pressure. There's different units for pressure. Some of those you might be familiar with. Millimeters of mercury is one unit of pressure, and gas pressures are typically measured with barometers. Another type of unit for gas pressure is atmospheres, and that's the abbreviation for atmosphere, just ATM. We're familiar when we measure the gas pressure in our tires with PSI, right? Pounds per square inch. That's a measure of pressure. And there's also something called a Pascal. That's another unit for measuring pressure. And it's going to be important. There are others as well, but the most common ones you're going to see in chemistry are millimeters of mercury and ATM. And it's important that you understand how to convert between those two units. And the conversion is that 1 atmosphere is equal to 760 millimeters of mercury. And so you would use that relationship just like 1 yard is 3 feet, right? So that if I told you something was a certain number of feet, you could likewise calculate how many yards it was. So that's going to be a somewhat important conversion to remember when we're dealing with gas pressures. Now, in moving on, there is an equation, and it's known as the ideal gas equation. And this is the ideal gas equation. PV equals nRT, where P stands for pressure, V stands for volume, N is a measure of amount, R is the ideal gas constant, and T is temperature. And some of those it just makes sense that that's what they measure. But what's important to note about PV equals nRT is what kind of units you use for each of the variables. And the way I like to do it is to always work with the same units. The first thing I'm going to tell you is what the ideal gas constant is. Now, there are different numbers for the ideal gas constant, and they change depending on what units they have. The ideal gas constant I always like to use is 0.0821. That's the number I always use for R. And the units for this ideal gas constant are liters times atmospheres per mole times Kelvin. Okay? And that is the units that I always use whenever I use this ideal gas constant. The units of that tell you what the units of everything else should be. Pressure should always be in atmospheres. Volume should always be in liters. Amount will always be in moles. MOL is the abbreviation for mole. And temperature should always be in Kelvin. So there's some things you want to look for and be careful about. Oftentimes, pressures are given in millimeters of mercury. So you've got to remember to convert to atmospheres, which is what we just went over on the previous slide. It's very common that volumes will be given in milliliters. You've got to convert it to liters in using this ideal gas equation. Amounts, watch for those to show up in grams. If it's in grams, you have to use the molar mass to convert it to moles. Temperature. Temperature is most commonly reported in degrees Celsius, so you've got to convert that to Kelvin. And recall that to go from Celsius to Kelvin, you simply add 273. Okay? Now, in coming up with this ideal gas equation, PV equals nRT, there's a couple of other gas laws that we want to go over. And the first of those that I want to talk about is Boyle's law. And each of these gas laws, what we do is we look at two of those variables. We've got P, V, N, and T, right, over here in our ideal gas equation. And what each gas law does is just takes two of those variables. It holds the other two constant, okay, and it takes two of those and looks at how changing one affects the other. For example, for Boyle's law, it compares pressure and volume. So, in other words, we're going to change pressure and see how it affects volume. In comparing pressure and volume, we have to hold what constant? If P and V are going to be compared, then that means the N and the T are held constant. So we're at a constant temperature and a constant amount of gas. Okay, notice I'm not referring to R because R is a constant. So it's always constant in these equations. So think about it, Boyle's law. How would pressure and volume relate to each other? If you had a syringe that was closed on one end and you pushed on that syringe, you know that at a certain point initially you're going to experience some resistance. And the more you push, the more resistance you're going to feel. Well, if that syringe is closed, when you start to push on it, you're decreasing the volume. So the volume is going down. That resistance you feel is the pressure. The pressure goes up. As the volume goes down, the pressure goes up. So what we say, pressure and volume, if one goes up while the other goes down, we say that that is inversely proportional. When one thing increases while another decreases. Mathematically, what we would write is that pressure is proportional to 1 over volume, and that means is proportional to. So as V gets larger, and it's on the denominator over here, that would make the calculated pressure become smaller. And that's Boyle's law. Okay, the next gas law we're going to examine is Charles' law. It's actually known as Charles and Gay-Lussac's law. And this law compares volume and temperature. So if we're going to just compare volume and temperature, then the pressure and the amount are going to be held constant. So what happens with volume and temperature? As a gas is heated up, as you increase the temperature, what do you think happens to the volume? Doesn't the volume likewise go up? So since volume increases and temperature increases, we would say that these are directly proportional to each other. And we would write that like this. Volume and temperature are directly proportional. As one goes up, the other goes up as well. Okay, and the last one we're going to look at, it goes along with Avogadro's law. And it compares the volume and the amount of a gas. As you increase the amount of a gas, you're going to likewise increase the volume. As you decrease the amount of gas, you're going to decrease the volume. So again, we would say these are directly proportional, and mathematically we would write that volume is proportional to N. Okay, and there's a lot of practical examples of the gas laws. Avogadro's law, when you blow up a balloon, you are increasing the amount of gas that you put into the balloon. As you increase the amount, N, likewise the volume of the balloon gets bigger. And it's maintaining constant pressure, okay? It's in equilibrium pressure with the air. If the pressure builds up too much, obviously the balloon's going to pop. Charles and Gay-Lussac's with volume and temperature, a hot air balloon's a great example of that. As you increase the temperature, okay, there's the little flame underneath the balloon that warms it up, the volume likewise increases in the gas. We know hot air rises, right? And that's related to gas density, which we'll get to later. A great example of Boyle's law would be pressure and volume. And if any of y'all scuba dive, if you ever been scuba diving, the deeper you go into the ocean, there's more pressure on the body of the scuba diver. And what that makes happen is the gas that is dissolved in their blood, the increase in pressure makes the volume of that gas much smaller. And so if the scuba diver goes to the surface really quickly, the pressure, as they start to rise to the surface of the water, the pressure very quickly starts going back down. Therefore, the volume of the gas that's dissolved in their blood very quickly expands, and this can be very painful. It can actually result in death as well. But that's Boyle's law. Now, all of these relationships together, if we look at Boyle's law and how pressure and volume are inversely related, and Charles' law that volume and temperature are directly related, and Avogadro's law that volume and number of moles are directly related to each other, all these combine together to give us the ideal gas equation. So let's combine all this and work let's do a calculated problem. Okay, if a sealed 15-liter tank is filled with 24.6 grams of propane at 27 degrees Celsius, calculate the pressure of the gas in the tank. So let's look at what we know. If we have our ideal gas equation, we know that we've got a pressure, volume, amount, the ideal gas constant, and T. So let's read through our problem and assign our numbers with what variable they go with. If you have a 15-liter tank, that is the volume. The 24.6 grams is the amount. 27 degrees Celsius is the temperature. And pressure is what we're calculating. We know that R is 0.0821 liters times atmospheres per mole Kelvin. Now, where do you want to start? We can't just start plugging numbers into the ideal gas equation, because we know that that amount has got to be in moles, and that temperature, Celsius, has got to be converted to Kelvin. So if we take 27 degrees Celsius and add 273 to it, we would have a Kelvin temperature of 300 Kelvin. And likewise, we've got to take that 24.6 grams of propane, and we have to convert that to moles using the molar mass of propane, which is 44.11 grams, because there's 3 carbons, right? 12.01 times 3, plus there's 8 hydrogens, and each one of those is 1.01 grams. That gives us a molar mass of 44.1. And then we divide that out, and so I know that I have 0.5577 moles of the propane. So I know this is 0.5577 moles. And now we're ready to plug in. Pressure is equal to moles what, I'm going to run out of room, I know, so I'm going to go over here and say P is equal to nRT over V. So P is going to be equal to N, 0.5577 moles, times R, which is 0.0821 liters times atmospheres per mole times Kelvin, times the temperature of 300 Kelvin, divided by our volume, which we said was 15 liters. And so we would calculate a pressure of 0.916. What? Do you see what the units are? Moles cancels. kelvins will cancel, liters will cancel, so our units are atmospheres. So the answer to that problem is 0.916 atmosphere. That is an extremely basic ideal gas equation problem. Okay, now I'm going to add a second part to this problem. Let's calculate the pressure if we increase the temperature to 58 degrees Celsius. So realize we're still dealing with these conditions. We've got the same 15-liter tank. We still have 24.6 grams of propane in it, but whereas over here we calculated it at 27 degrees Celsius, okay, we calculated this pressure, 0.916, I'm now asking you to calculate, well, what would the pressure be at 58 degrees Celsius? Okay, obviously, you can still use this equation, PV equals nRT, because you still know the amount and you know your ideal gas constant, and it's the same volume. But I want to show you how to work this one a different way, because sometimes you'll be given a problem like this where you're given the starting pressure that we just calculated of 0.916, the starting temperature of 300 Kelvin, and this final temperature of 58 degrees Celsius. So you don't know an amount. You cannot use PV equals nRT if you don't know the amount. Okay? What we have here is we've got information about a gas under two sets of conditions. The first set we've already done calculations on, okay? We've already used PV equals nRT and did some calculations with that first set of information. So since that was the first set of information, I'm going to give all these a 1 because those went with the information in the original problem, okay? Now, if I were to take this PV equals nRT and to put everything on one side, if I divided this side by nRT, well, I would likewise have to divide this side by nRT. And what I would have is that P1, V1 over N1, R1, T1. And those ones are there because it's the gas under the first set of conditions. It's going to be equal to what? Well, do you see that this same equation would apply to this gas under the second set of conditions? So in other words, it would be equal to P2 times V2 over N2, R2, T2. Okay, and so when you're working this kind of combined gas law equation, this is how you want to start to set it up. Look at these two equations. Are there any variables where they're the same on both sides of the equation? Well, R1, R is 0.0821. Well, R2 is also 0.0821, so those variables are the same on both sides of the equation. I'm going to eliminate those. The volume will be the same because the original problem said it's a 15-liter tank. And in this question, we're just saying the same tank, we're just going to increase the temperature. So since it's a 15-liter tank, and that's not changing, then V1 and V2 are the same. The amount of gas is not changing either. We've got the same amount of propane. Pressure is changing because the problem says calculate the pressure when we change to this temperature. So that's another way to approach it. We can see that pressure and temperature are the only thing changing. And what we have done is derived P1 over T1 is equal to P2 over T2. What is P1? The original pressure is 0.916 atmospheres. What is T1? We were told in the original problem the initial temperature is 27 degrees Celsius, which we calculated to be 300 Kelvin. What is P2? That's what we're calculating. Calculate the pressure. T2 at this temperature at 58 degrees Celsius. So I would have to add 273 to that. Don't make the mistake and leave it in Celsius. And that's going to be 331 Kelvin. So mathematically, to solve that, I'm going to cross multiply and say 331 times 0.916 Then I'm going to divide both sides by 300. What do we expect to happen? If we increase the temperature to 58, what do you expect the pressure to do? I expect it's going to go up because I've heated this gas up. And indeed, my calculations show that the pressure goes up to 1.01 atmospheres from its original 0.916. So our calculations fit what we expected would happen, that if we increase the temperature, the pressure would likewise increase.